All right, welcome honor students. This is your honors lecture on percent yield and percent purity. You have previously just learned about the mole and how we can use the mole and perform dimensional analysis with the ratios given to us, known as the molar ratios, through the coefficients, the big numbers in front of molecules in a reaction. And so what we do is when we quantify the relationship between reacting chemical species and the resulting produced, I should say, chemical species, what we can see is that we can use those numbers as long as we are in the mole, the universal unit to compare other substances. We can use those molar ratios, those coefficients, to actually predict, given this amount of starting, how much can I make of this product? That's known as yield, right? What I yield, what I get out of the process. So we know that theoretically, we have a predicted amount. According to our perfect ratio, our molar ratio, our balanced equation, we can predict an amount that will come out. This is our theoretical yield. So the theoretical yield is the amount of product produced based on molar ratios, which is known as, right, our coefficients, and stoichiometry, which is the mathematical process of using molar ratios. So this is the amount of product produced based on molar ratios, the coefficients, and stoichiometry, assuming the reaction goes to completion 100% of the time. Okay, so there's a reason that we say it's theoretical. Like all things being perfect, this is what our math tells us that we should get. But here's the catch. The reality is that most reactions don't produce the theoretical yield. Reality is most reactions don't produce the theoretical yield amount. This is because of various reasons. One, we have what we call a limiting reagent. That means we don't have enough of both reacting chemical species in the perfect ratio. Like somebody's gonna run out first, right? Run out of first. Two, right? We have side reactions. Okay, what we call side products. Okay, remember collision theory, how all molecules have to collide in the correct orientation, the correct positioning, and with enough energy. And maybe have I introduced this to you? Anyway, maybe I have, maybe I haven't. But either way, there's this theory that tells us that when particles react, they have to collide in a specific way to produce a chemical reaction. Okay. And if we don't collide in that way, what happens is that we can actually break the bonds in different places than we want them to be broken. And that means that we connect the bonds in a different way than we want it to be connected, right? So we actually get products that we don't want. That's side reactions or side products. Two, sometimes the reaction just like flat out doesn't work. I've had days in lab and my chem professor would tell us that there are some days that where like no matter how much theory there is in science, there's some days where just the molecules do not want to work with you and no one can really explain why. It could be some unknown condition abnormality. Maybe your room was just a degree temperature above what you needed it to be. Like maybe the reactions are old, but like they're new and you're just like, why? So there's always just the fact that sometimes reaction just like straight up doesn't work. Okay. And then of course, sometimes we discover that the reaction undoes itself. It decomposes. And this is just like some of the issues that could be contributing to the reality that our stoichiometry based, our molar ratio based predicted product amount, theoretical yield, is never actually met in lab. So we're going to talk about two, maybe not even two, maybe just one of the ways that we account for one of these sources of error. And we're going to focus on limiting reagent. So the limiting reagent, all right, is the reacting species that you have the least of. Or another way of putting it, that runs out first. Okay? And then, of course, the excess reagent is the reacting species that you have extra, right? Or it's the one that remains left over after you react all that you can react. So how do you calculate theoretical yield based on limiting reactant? Well, let's start really simple. The overall process is that you identify the mole ratio, right? Using the balanced chemical equation coefficients, right? Mole ratio is, right? Remember that mole ratio is like saying coefficients of the balanced chemical equation. And then you use that mole ratio to determine which reactant will produce the least amount of the same product, right? So for example, let's say I have a recipe for ham and I say that I need 2 slices of bread for every 1 slice of meat. Okay, that's a very skinny sandwich. But let's say you're on like a protein diet and you just are only eating carbs. I don't know. And so what we can say is that, well, 2 pieces of bread will get me to 1 sandwich. That's a unit conversion, right? 2 pieces of bread will get me 1 sandwich. Or 1 sandwich requires 2 pieces of bread. Okay. And so, and then what we can say is, well, I also know that I need 1 slice of bacon, I don't know, bologna, for every 1 sandwich, or 1 sandwich requires every 1 bologna. Now, just based off of the recipe, not even looking at our materials yet, not even looking at what we actually have in stock, just based off the recipe, we would probably say that most likely the slices of bread is our limiting reactant or a limiting reagent, the one that we're most likely going to run out of first, because I need 2 of it to produce 1. Whereas the bologna, the B, okay, is most likely, you know, depending on what's back in stock, most likely would be the ingredient, the reagent that we would probably have in excess. Why? Because I only need 1 to get 1 sandwich, right? When we compare getting 1 sandwich, it's the bread that we need more of to actually get to that 1 sandwich. Now, what we could say then is we could use the molar ratio of the limiting reactant and product to calculate the grams of sandwich produced, or the amount of sandwiches produced. Now, why do we use the limiting? You can't make a sandwich if you run out of its ingredients. So the moment you run out of one of those ingredients, you're stuck. You can't make just like piles of bologna slices. That's not a sandwich. That's just like a bunch of bologna slices, right? So we use the limiting reactant to calculate how many, or sandwiches or whatever, usually in grams, because remember, in chemistry, we want to be able to sell the product that we make, and we don't sell the product in molds, we sell it in grams, right? And so what we might say as well, I know that for every 2, okay, some X amount that I start with of A, I know that to make a sandwich, unit conversions, right? And here we're treating our substances almost like a unit. For every 1 sandwich, I need to use up or require 2 A's. And then we would multiply that across, multiplies across bottom, and we get some number of sandwiches. And then what we would do is we'd say, well, using the molar mass, right? Molar mass, which is, right, grams per mole, I get some number of grams of sandwich or whatever your product is. So that's kind of the overall process. The value in grams of your product is your theoretical yield. This is based on like what you have, what you'll run out of first. This is the most you can get. And this is still assuming a lot going right. This is still assuming a lot. Like even theoretical yield accounting for the limiting reactant is still assuming a lot. We don't even get the theoretical yield amount based on limiting reactant ever in lab. Like this is just getting us halfway to more of reality. Like accounting for your limiting reactant is just like a half step toward the more realistic reality that we don't get very much yield at all, usually in lab, because sometimes molecules just hate us. So what would this look like now putting values in? Let's say I start with 1 gram of each reactant in this synthesis problem. I have for every 2 atoms or moles, right? 2 moles of silver metal, I need 1 mole of diatomic iodine to produce 2 moles of silver 1 iodide. Okay. And so the question is, if I start with 1 gram of each reactant, how much silver iodide could you make? Now, looking at this equation, you probably would predict that silver most likely is the limiting reagent. But here's the thing. We are now going to add in the step of, okay, now let me actually check what's in my pantry, right? Let me check what I actually have available to me, because I might realize that I just have a ton of silver and no iodine. And even though the recipe doesn't call as much for iodine, and that would be upon first glance, the excess reagent, it might end up being my limiting reagent if I just straight up don't have enough in stock. So I'm told that I start with 1 gram of each reactant, 1 gram of silver, 1 gram of iodine. So I'm going to calculate the theoretical yield based on each. Okay, now I can never compare substances in grams. So I'm going to convert 1 gram of each substance to moles of each substance. So 1 gram of silver times, okay, so silver has a molar mass of 107.89 times 1 mole per 107.89 grams gets me to moles of silver. So 1 divided by 107.89, and I get a value of 0.00928, or I'm going to say 927. Okay. We technically, actually, you know what? I'm gonna make it longer. So 9269, because I don't want to quite cut off at sig figs yet, right? I'm starting with a 3 sig fig problem. I don't want to round too early in the process. So this tells me moles of silver. Now, I know according to the balanced chemical reaction that for every 2 moles of silver, right, molar ratio, I make 2 moles of AgI. So that means I'm going to get 0.00927 moles of AgI. Okay, so that's my theoretical yield. I'll convert to grams later. Let's just hold off until I can compare it to the other reactant. So that's what silver can make. Based on the silver in the pantry, this is what I can make, my theoretical yield based on this reactant. Now let's try the other reactant. So let's say I have 1 gram of now diatomic iodide. The molar mass to get it into moles to actually compare it is iodine is 126.9, and I have 2 iodines. So that means my molar mass of diatomic iodine is 253.8 grams per mole. That gets me a value of 1 divided by 253.8 grams of 0.0039 moles of iodide. diatomic iodide. And I know according to my chemical reaction that, well, for every 2 moles of AgI I produce, I need 1 mole of I2. And that means I get a value of 0.007, 0.00788 moles of AgI. So when you look at these numbers, what you see is that Ag is not our limiting reagent like expected. Hold up, it's not our limiting reagent like expected, because in the end, I actually have to look at the pantry to see how much of each ingredient I have. The recipe just tells me a general ratio that I can use. But in the end, if I can have the recipe all day, and if I don't have enough ingredients in the back, it ain't gonna happen no matter what. So this is a nice little problem to remind you that even though the technique I taught you at first, which is just a really passing glance technique of, well, most likely this would probably be the limiting reactant. Don't forget that you have to use the data given to you. If I tell you I have 1 gram of each reactant, you actually have to follow through the entire process of the stoichiometry to actually see which reactant is truly your limiting based on how much of it you actually have in the back room, in the stock room. So here we see that it's actually iodine that ends up being the limiting reagent. I get less moles of product. And now all I have to do is take that moles of product and turn it into grams of product. So I do 0.00788 moles of AgI times the molar mass of AgI, which is 126.9, clear, 126.9 plus 107.89, and I get for every mole of AgI, actually I want to put moles on bottom. Sorry, for every mole of AgI, I have 234.79 grams and 234.79 grams. And that means I actually get 0.00788. I actually produce my theoretical yield, given that a lot of other things are going right too, is 1.853 sig figs grams of AgI. And that is my final answer. That's my theoretical yield based on the actual limiting reactant, based on molar ratios and how much of supplies I have in the actual stockroom. So now let's account for another type of error, okay? We're gonna go back to, well, what if you have other issues? Like straight up the reaction just like doesn't work, right? Or you get side products, right? What about those errors? How do we account for that? And how do we account for sometimes there's just like contamination, right? Side products, or maybe our products weren't very purified before in the first place that we used, right? Well, we have 2 more calculations that are very simple, known as percent purity and then actual yield. So let's say you have an impure substance, okay? An impure substance is a substance that's been contaminated by the presence of an undesired compound. Okay. So what we can do is we can actually calculate the percent purity by mass. So what we say is that, oops, and I think I meant to delete that. So oops, not actual yield. We have a different calculation for actual yield below. So, well, I guess it is kind of the actual yield. Just kidding. I'll keep it, because the actual yield is how much you actually got of the product, which would be a good indicator of how pure it is in the first place. So actually, you know what? I'll keep that. So percent purity, or if you want to think about it from this term of actual yield by mass, is calculated by saying however many grams of desired product I get, desired product, all over the grams of total sample, right? with the impurity, total sample impure. I'll put even impure sample. Total impure sample times 100. If you're like, this is sounding awfully like a percentage, you are absolutely right. You are completely right. So practice problem, determine the percent purity or the actual yield of the desired product I get if a 4.5 gram piece of carbon is purified and only produces 3.8 grams of pure calcium metal. Okay. Oh, sorry, piece of calcium. Okay. So I get some chunk of calcium that I'm like, I don't know if this is actually like fully calcium. And then when I purify it, I get 3.8 grams after the process. So what's my percent purity? What's my actual yield by mass? Well, I have 3.8 grams pure desired product, pure calcium. And I started with a sample of impure mixed with contaminated, other undesired presence of compounds of 4.5 grams of impure calcium times 100. And I should get a purity, percent purity or actual yield of 3.8 divided by 4.5. Okay. Which is 84%. According to sig figs, right? Two sig figs, 84%. So my percent purity is that out of that sample, that 4.5 gram sample, 84% of it was truly pure calcium. And that was determined by actually purifying it and seeing how many grams I actually got of pure calcium. So now there's another thing I want to add is that actual yield can be used, right? The amount that you actually get, amount of desired product you actually get in lab. Okay. The actual yields can also help us calculate another thing known as percent error. Now, this involves comparing not an impure substance, but comparing, okay, what was our theoretical amount? What was the amount that we actually got? How much did we mess up? How much did we lose? How much did we not meet? Okay. So percent error is a very similar calculation. And here it tells us, and we tend to do it by mass, but you could do it by a lot of different units as long as you keep it in the same unit. But let's say by mass, percent error by mass tells us the grams, okay, the theoretical gram yield, and I'm just gonna actually say theoretical yield, which is always greater than your actual yield. And if your actual yield is ever greater than your theoretical yield, you know that you have an impure sample. Okay, so sometimes these pair up. So your theoretical yield minus your actual yield. Okay, so what's the difference between what you thought you would get and what you actually got all over your theoretical yield? Times 100. That tells us our percent error. How much did we not get? How much mess up did we have? How much incomplete reaction or side product reaction or non-reacted, right, parts of the reaction did we have? So for this problem, let's say that based on our problem above, we predicted that we should have gotten our theoretical yield in grams was 1.85 AGI. Okay, that's what we got from above. But we are told that our actual yield, what we actually got in lab is 1.50 grams of AGI. So for percent yield, we're going to say theoretical minus actual. So 1.85 minus 1.50 grams, right? All over, what was our theoretical? 1.85 grams times 100%, right? And what that gives us is that our percent error, 1.85, I should be able to do this in my head, 0.35 divided by 1.85 is we have an 18.9% error margin. So 18.9% of our reaction didn't work for multiple different reasons, okay? Which would be discussed in like error analysis or sources of error or whatever. This would be our percent error yield. Like how much error did we actually create in the process of doing this reaction. So what about this one? When XX hydrochloric acid is HCl, is added to a contaminated calcium carbonate sample, 2.49 grams of carbon dioxide is obtained. Write the balance equation and find the percent purity. So I have hydrochloric acid, which is most likely aqueous. Okay, it's probably in a liquid solvent, water solvent. And it reacts with contaminated calcium carbonate, CaCO3. Again, probably, actually, you know what? That probably is a solid. And what it does is it produces, okay, carbon dioxide. And I think water, let's see, does it produce this? Carbon dioxide and water, and I think it also produces CaCl. Okay, so how would we balance this, right? And you know what? Before I go any further, low-key, I'm just gonna check that I did this right. So hydrochloric acid and calcium carbonate. Let me make sure that I did this right, because that would be a little embarrassing. Hydrochloric acid and calcium carbonate produce CaCl2. Oh my goodness gracious, even I'm floundering. CaCl2, water, and carbon dioxide. Perfect. So I'm gonna move that over, and I need to balance it. So let's see, how do we balance this equation? Well, I have one calcium and one calcium. I need two carbons. So that means I got two hydrogens and I have three oxygens. Perfect. All I needed was a 2 in front of HCl to be balanced. Here we go. Okay. So that's my balance equation. All right. And then all I tell you is that I want you to find percent purity. Okay. So percent purity is, okay, how much did I have of the sample and how much did I get out? So what we see is that when we add 5.73 grams of contaminated calcium, we get 2.49 grams of carbon dioxide. So the question is, what's our percent purity of the calcium carbonate? So we need to figure out, well, what was the theoretical yield, okay, that of calcium carbonate that we needed to use, or I should maybe say, what was the theoretical amount of potassium carbonate, sorry, calcium carbonate that we need to use to get pure carbon dioxide? So here we're actually working backwards. So I'm starting with, I know I have 2.49 grams of pure carbon dioxide produced, but I started with impure, okay, calcium carbonate of 5.73 grams. The question is, well, how much pure calcium carbonate reacted to produce pure carbon dioxide? So I'm going to start backwards. I'm going to say, okay, I have 2.49 grams of carbon dioxide. I know that for that product to be made, I need to first get to moles. So for every mole of carbon dioxide, I need, oh, I should really know this in my head. 16 times 2 is 32, 44, about 44 grams of CO2. So 2.49 divided by 44. And I get that, okay, that equals 0.056 59 moles of CO2. Okay. And I know that in order to produce that amount of CO2, I needed, according to my balanced chemical equation, I needed 1 calcium carbonate to react for every 1 CO2 produced. So I would say that my theoretical, not yield this time, but my theoretical amount of reactant that I needed is 0.5659 moles of CaCO3. Okay, that's how much pure CaCO3 I needed to actually produce pure carbon dioxide product. So what my telling me is that what would this be then in grams? Because in the end, I want to go by gram amount. So I say, well, calcium carbonate has a molar mass, okay, of 100.09 times for every 100.09 grams of calcium carbonate, I have 1 mole. And so it's times 100.09. And I get that, well, that means that 5 point, and here, let me put this another color, 5.664 grams of pure calcium carbonate reacted. So going back to my actual question, well, what was the percent purity of the calcium carbonate? So working backwards from the product amount, I was able to find how much theoretical amount of calcium carbonate I needed to actually react pure calcium carbonate. I need to react. And then I say, well, the percent purity then is that I started with impure, okay? I started with impure 5.73 grams of impure calcium carbonate. But I know according to my reaction, I reacted to produce 2.49 grams of carbon dioxide. I required 5.664 grams of pure calcium carbonate to actually react. And what I get is that my times 100, what I get is that my percent purity of the original sample of reactant calcium carbonate is 5.664 divided by 5.73. And that means my original sample was 98.9% pure calcium carbonate. And that's how you would do that problem. Kind of a doozy, but it's also math, right? It's following a flow. And the number one way you prevent yourself from making a mistake is track your units. And this time your units not only include grams and meters and liters and all those SI units, but it now includes your substances. Make sure you end up in the same substance, right, that you want. So really good work, you guys. There are a couple workbook problems. Actually, I think several workbook problems for you to work on. This would be a topic that you really want to pour practice into, and you want to come see me during seminar, lunch, before school, after school to talk about it and do practice problems with me or a friend. All right, good luck, everybody. See ya.